welcome to this problem walkthrough. In this session, we'll explore a fascinating coding challenge titled Count Substrings That Differ by One Character. Together, we'll break the problem down, analyze different approaches, and discuss their complexities. Let's dive in. In this problem, we are tasked with comparing two strings, s and t, and counting all the pairs of non-empty substrings that differ by exactly one character. A substring is simply a sequence of consecutive characters within a string, and for two substrings to qualify, they must have the same length and differ in exactly one position. For example, the substrings cat and bat would qualify because they differ only at the first character. Our goal is to calculate the total number of such pairs across all possible substrings of s and t. The output will be a single integer representing this count. To begin, we are given two strings s and t, with lengths n and m respectively, as input. The constraints ensure that both strings consist of lowercase English letters, and we need to ensure our solution is efficient given the potential number of substring comparisons. To better understand the problem, let's look at an example. Suppose s is ABA and t is BABA. First, we list all the non-empty substrings of both strings. For s, we have 6 substrings, a, b, a, ub, ba, and aba. For t, we have 9 substrings, b, a, ba, ub, bab, aba, and baba. Now, we look for pairs of substrings, one from s and one from t, that differ by exactly one character. For instance, the substring pair, a, b, qualifies because a and b are different in one position. Similarly, a, ba, qualifies because they only differ at the first character. In total, we find 6 such pairs, a, b, a, b, ub, ba, ub, and aba, baba. Therefore, the output for this example is 6. Now, consider another example where s is ab and t is bb. The substrings of s are a, b, and ab, while the substrings of t are b, and bb. We then compare these substrings to identify pairs that differ by exactly one character. For this input, we find 3 pairs, a, b, where a and b differ in one position, b, where the substrings are identical except for one position in their structure, and a, b, where the first character differs. Summing up, the total count of such pairs is 3, so the output for this input is 3. Finally, let's look at a simpler example where s is a and t is also a. The only substring of both s and t is a. Since a and a are identical, there are no pairs of substrings that differ by exactly one character. As a result, the output for this case is simply 0. This highlights that if the two input strings are identical or consist of the same single character, there will be no valid pairs that satisfy the condition. To wrap up, let's discuss the constraints and edge cases. The lengths of s and t are bounded between 1 and 100, which means the solution must handle a potentially large number of substrings efficiently. Both strings consist of lowercase English letters, so we don't need to account for special characters or case sensitivity. Edge cases include minimum input sizes, such as when both strings have a length of 1. In this case, if the characters are identical, the output is 0. For strings with all identical characters, no valid pairs will exist. Additionally, for maximum input sizes, the solution must efficiently compare substrings without exceeding time limits. Finally, cases like s equals abc and t equals bbc may produce overlapping pairs, so it's crucial to handle these systematically to avoid double counting. This ensures the solution remains both correct and efficient. To start, let's consider the brute force approach. The intuition here is straightforward. We check every possible pair of substrings from s and t to see if they differ by exactly one character. For a substring of length k and s, we compare it to all substrings of the same length in t. By comparing characters one at a time, we count the mismatched pairs where there's exactly one differing character. However, the computational expense of this approach is significant. Extracting substrings for both s and t takes O, n squared, and O, m squared, respectively, and comparing them adds another layer of complexity. This results in a time complexity of O, n squared times m squared times k, making it highly inefficient for larger inputs. While simple to implement, this method is impractical when n and m are large, such as 10 cubed or higher. Now, let's explore the optimized sliding window approach. This method reduces redundancy by efficiently identifying substrings that differ by exactly one character. The key idea is to use two pointers to expand substrings from each starting index pair, I, J, in S and T, while keeping track of mismatches. A key observation is that two substrings differ by exactly one character if there's only a single mismatch in their corresponding characters. By maintaining a mismatch count as the substrings expand, we can stop as soon as mismatches exceed 1. The implementation involves iterating through all valid starting indices of S and T, expanding substrings, and incrementing the result count whenever we encounter exactly one mismatch. This approach achieves a time complexity of O and *m, since we process each starting pair linearly. It avoids redundant comparisons while ensuring efficiency, though it does require careful management of the mismatch count. Next, we have the dynamic programming approach, which offers another way to optimize the solution. Here, we use a DP table to store information about mismatches between substrings of S and T. Specifically, let dp I, j represent the number of substrings of S, 0i, and T, 0j, that differ by exactly one character. The transition works as follows: if the characters S, I, and T, j match, then the value of dp I, j is carried over from dp I1, j1. Otherwise, we increment the count to reflect the mismatch ending at I, j. By filling out this table row by row, we can iteratively calculate the result. While the time complexity is O and *m, the space complexity depends on whether we store the entire table or just the last row. This approach is elegant and avoids redundant calculations, but it does require extra memory to maintain the DP table, which can be a limiting factor for large input sizes. Finally, the chosen strategy is the optimized sliding window approach. This method strikes the right balance between simplicity and efficiency, achieving a time complexity of O and *m, without requiring additional space. These properties make it well suited for larger inputs. While the dynamic programming approach is a strong alternative, it was not selected due to its higher space complexity. As for the brute force method, it was ruled out entirely due to its impracticality for larger input sizes. By leveraging the sliding window technique, we efficiently count mismatched substrings without redundant comparisons. This approach adheres to the problem's constraints and provides an elegant, scalable solution to the task. In this problem, we are given two strings, S and T, and our task is to count the number of pairs of substrings, S_sub, T_sub, that differ by exactly one character. Specifically, each pair must satisfy four conditions. First, S_sub must be a substring of S, and similarly, T_sub must be a substring of T. Second, the substrings must have the same length. Third, we compare the characters of S_sub and T_sub at each position, and only pairs with exactly one differing character are valid. Now, to approach this, let's start with the brute force method. First, we generate all possible substrings of S by iterating over its starting indices. At each starting index, we generate substrings of increasing lengths. Next, we repeat this process for T, generating all its substrings as well. This sets us up to compare substrings from both strings in the subsequent steps. After generating all substrings, the next step is to compare substrings of the same length. For every pair of substrings, S_sub, T_sub, we compare their characters one by one. During this comparison, we count the positions where the characters differ. If this count is exactly 1, we consider the pair valid and include it in our total count. Once all pairs are processed, we return the total count of valid pairs. However, this brute force approach is computationally expensive because it involves generating substrings and performing pairwise comparisons, leading to a high time complexity. To optimize this, we can avoid explicit substring generation. Instead, we directly compare matching windows of S and T using their starting indices. By iterating over all possible starting indices I in S and J and T, we can streamline the process and reduce redundancy. In the optimized approach, instead of creating substrings explicitly, we use a sliding window technique to compare characters directly. For each pair of starting indices, I, j, and a given substring length k, we compare the characters of S, I plus k, and T, j plus k. A counter keeps track of the number of differing characters in this window. If at any point the difference count exceeds 1, we stop comparing further for that pair, leveraging early termination to save computation. On the other hand, if the difference count is exactly 1 by the time we finish comparing the window, we increment our valid pair count. Additionally, we account for edge cases such as when either S or T is empty, or when all characters in both strings are identical, both of which result in a count of 0. There are several key insights that drive this optimized approach. First, instead of explicitly generating substrings, we use sliding windows with 2 nested loops and offsets, which significantly reduces overhead. Second, we perform character-by-character matching within these windows, avoiding the extra memory cost of creating substring objects. Third, we optimize further by ensuring only substrings of the same length are compared, eliminating invalid comparisons. Finally, the time complexity improves dramatically. While the brute force approach has a complexity of O, n cubed asterisk m cubed, where n and m are the lengths of S and T, the optimized approach reduces this to O, n squared asterisk m squared, by avoiding redundant substring generation and leveraging early termination during comparisons. To implement this efficiently, we rely on a few simple data structures and techniques. A basic integer counter tracks the differing characters between substrings during comparisons. Additionally, the two-pointer technique allows us to iterate over S and T directly, enabling character-by-character comparisons without generating substrings. For example, if we take the input S equals ABA and T equals BABA, we start by comparing substrings. Let's take S underscore sub equals A from S and compare it with substrings of T. For T underscore sub equals B, the pair differs by exactly 1 character, so it's valid. However, with T underscore sub equals A, the pair has no differing characters, making it invalid. This process continues for all possible substrings of both strings. We extend this comparison process to longer substrings, such as AB and ABA. For each pair of substrings, we count the differences and determine validity. For the example S equals ABA and T equals BABA, the total count of valid pairs comes out to 6. The output of the algorithm in this case is therefore 6. This example demonstrates how the optimized approach efficiently handles substring comparisons while minimizing redundant computations. By leveraging sliding windows, early termination, and character-by-character matching, we achieve a solution that is both time-efficient and memory-efficient, making it well-suited for larger input sizes. This solution follows a systematic approach to count all substrings between S and T that differ by exactly 1 character. The problem is tackled using a helper function count_diff that calculates the number of valid substrings starting at specific indices I and S and J and T. The count_diff function initializes 2 variables, diff to track the number of differing characters and count to store the count of valid substrings. As it iterates over the characters of S and T simultaneously, it increments diff whenever a mismatch is found. If diff equals 1, it means the substrings differ by exactly 1 character, so count is increment. If diff exceeds 1, the loop is terminated, as no further substrings starting at these indices can be valid. In the main function, nested loops iterate over all possible starting indices I and S and J and T. For each pair, I, J, the helper function count_diff is called to calculate the number of valid substrings starting at these positions, and this count is added to the total. The solution is efficient for moderate input sizes, as the nested loops and sliding window approach ensure that the complexity is manageable. This approach guarantees that all valid substrings are counted without redundancy. Here, we define a class called solution and implement the main function, countSubstrings. This function calculates the total number of substrings in 2 strings, S and T, that differ by exactly 1 character. We start by initializing a variable, total, to keep track of the overall count. Then, we use 2 nested for loops to iterate through all possible starting indices in both strings. For each pair of starting indices, we call a helper method, countDiff, to calculate the count of valid substrings beginning at those indices. Finally, the total count is returned as the result of the function. The key idea here is to systematically compare substrings at every possible starting point between the 2 strings. The countDiff helper function focuses on counting substrings starting at specific indices, I and J, in strings S and T, respectively. We initialize 2 variables, diff, to track the number of differing characters, and count, to accumulate the count of valid substrings with exactly 1 difference. Using a while loop, we expand the substring comparison as long as the indices remain within bounds. For each character comparison, if the characters differ, we increment diff. If diff equals 1, we increment count, since this means the current substring has exactly one differing character. However, if diff exceeds 1, we exit the loop early, as we are only interested in substrings with exactly one mismatch. This function ensures we efficiently check and count valid substrings for the given starting indices. To solve this problem, we start by initializing a variable total to 0, which will track the count of substrings that differ by exactly one character. Then, we iterate over all possible pairs of starting indices, I, j, from the strings s and t. Here, I represents the starting index in s, and j represents the starting index in t. Both indices range across the lengths of their respective strings. For the first iteration, with I equals 0, j equals 0, we call a helper function count_diff to compare the substrings starting at these indices. Inside count_diff, we initialize diff to count character mismatches and count to track valid substrings. Comparing character by character, we see that s0 is at int, 0 is b, which differ, so we increment both diff and count by 1. However, the next comparison, s1 and t1, also differs, making diff exceed 1. At this point, we stop counting substrings for this pair. The function returns 1, which is added to total, bringing it to 1 so far. Now, moving to the next pair of indices, I equals 0, j equals 1, we again call count_diff to compare the substrings. Here, the first characters, s0 and t1, are both a, so there's no difference. Similarly, s1 and t2 are both b, and s2 and t3 are both a. Since all comparisons show no differences, the function returns 0, and the total remains 1. For the pair, I equals 1, j equals 2, we again call count_diff. Starting with s1 and t2, both are b. Similarly, s2 and t3 are both a. Again, there are no differences in the comparisons, so the function returns 0, leaving the total unchanged at 1. At the end of this example, after considering all possible substrings, the final output for the total count is 6. In the second example, the input strings are s equals abc and t equals def. Here, we compare all possible substrings of s with all substrings of t. Since every character in s differs from every character in t, and the differences exceed 1 for all substring pairs, the total count remains 0. Hence, the final output for this example is total equals 0. In the third example, we use the smallest possible strings, s equals a and t equals b. Comparing their only characters, s0 equals at int 0 equals b, we find that they differ by exactly one character. This qualifies as a valid substring pair, so we increment the count by 1. There are no other substrings to consider, and the final output for this example is total equals 1. Here, we analyze the time complexity of our solution. The solution employs two nested loops that iterate over the indices of strings s and t. If s has a length of m and t has a length of n, these loops contribute m*n to the overall complexity. Inside these loops, the count_diff function is called for every pair of starting indices, I, j, from s and t. This function compares substrings starting at s, I, and t, j, stopping when either one of the strings ends or more than one difference between the substrings is found. In the worst case, the function will iterate through up to min, j, characters. When summed over all possible starting indices, this results in a total number of comparisons equivalent to the sum of triangular numbers. Specifically, the worst-case total is represented as the double summation of min, j, for all valid I and j. This summation simplifies to a worst-case time complexity of m squared n, or m*n squared, depending on which string is longer. When the lengths of s and t are roughly equal, or m is almost equal to n, the time complexity becomes approximately n cubed. In the best or average case, early detection of differences allows the count_diff function to terminate sooner, but this does not alter the asymptotic complexity, which still depends on the lengths of the strings. Therefore, the final time complexity in the worst case is m squared n, or n cubed, when m is almost equal to n, while the best case complexity is m*n, if all differences are detected immediately. For space complexity, the memory usage is primarily determined by the input strings s and t, which together require O, M plus N, space. The count_diff function itself uses only a fixed number of integer variables, contributing O, 1, additional space. Hence, the total space complexity is O, M plus N. The given solution employs a brute force approach, as it exhaustively examines all possible substring pairs and compares them character by character to count differences. This results in high time complexity, especially for large inputs, due to the nested loops and repeated substring checks. To improve efficiency, optimized approaches such as sliding window techniques or dynamic programming can be utilized. These methods aim to reduce redundancy by reusing results from overlapping substring comparisons. Optimized algorithms can achieve a time complexity of O, M*n, or even better under certain conditions, significantly outperforming the brute force approach. In conclusion, while the brute force solution is straightforward, it is only practical for small strings. For larger inputs, adopting optimized algorithms is essential to achieve better performance and scalability. When tackling this problem, there are a few common mistakes to watch out for. First, many beginners fall into the trap of using a brute force approach, where every substring of S is compared with every substring of T. This results in a time complexity of O, n cubed * m cubed, which becomes infeasible for larger input sizes, such as 10 cubed or 10 to the power of 4. To address this, it's important to recognize when brute force is not practical and explore optimizations like sliding windows, hashing, or dynamic programming. Another frequent mistake involves off-by-one errors in substring comparisons. For example, miscalculating the ending index can lead to out-of-bound errors or missed substrings altogether. To avoid this, always pay close attention to the boundaries of your substrings and ensure that your indices align properly in nested loops. Lastly, edge cases are often overlooked, such as empty strings, single character strings, or cases where S and T are identical. Testing your code explicitly with these edge cases is essential to prevent incorrect results. Another area where mistakes frequently occur is in interpreting the requirement for exactly one character difference. Some solutions mistakenly allow no differences or more than one, which deviates from the problem's constraints. To address this, you can implement a helper function to count mismatches and verify that there is exactly one mismatch. Additionally, while optimizing, some solutions become overly complex, making them harder to debug and maintain. This can often be avoided by breaking the problem down into smaller, manageable components and using helper functions to keep the code clear and modular. Simplifying the structure of your solution not only helps during debugging but also ensures that your approach remains focused and efficient. To perform well in interviews, it's crucial to focus on a few key strategies. First, always understand the constraints of the problem. For example, ask clarifying questions about the size of S and T to determine whether a brute force approach is viable or if optimizations are necessary. Leveraging sliding window patterns is another effective strategy for problems involving substrings, as this technique helps reduce redundant comparisons. Pre-computation and hashing can also be powerful tools. Storing pre-computed values, such as substring hashes, can significantly accelerate comparison operations. Dynamic programming is particularly useful when the problem involves comparing substrings of varying lengths, as it allows you to store and reuse intermediate results. Finally, clarify all aspects of the problem requirements before coding. For instance, verify whether the comparison is case-sensitive or if special characters are included. This ensures your solution aligns with the expectations of the problem. Understanding related problems can provide valuable insights and help you draw parallels to other challenges. For instance, the current problem, LeetCode 1638, shares similarities with other substring problems, such as LeetCode 5, which focuses on finding the longest palindromic substring, and LeetCode 30, which involves substring concatenation. Another related problem is LeetCode 1062, which deals with finding the longest repeating substring. Exploring these problems can deepen your understanding of substring operations and common techniques. Among alternative approaches, the optimized sliding window is a popular choice. While it reduces redundant comparisons, it requires careful implementation to manage edge cases effectively. This technique is particularly useful when substring lengths are fixed or constrained. Another approach is dynamic programming, which, while requiring additional memory, significantly improves time complexity to O, n*m. This is especially beneficial when the problem involves overlapping subproblems, such as substring comparisons. Hashing is another alternative approach that can be incredibly efficient for substring problems. By pre-computing and storing hashes, you can speed up substring comparisons significantly, which is particularly useful when dealing with repeated or exact substring matches. However, it's important to consider the trade-offs. While hashing reduces the time spent on comparisons, it does introduce additional memory overhead. This method is especially effective when the problem involves comparing multiple substrings efficiently, as it allows you to avoid recalculating values repeatedly. Overall, hashing is a great tool to have in your arsenal for tackling problems that require optimizing substring operations. Thank you for joining me on this problem walkthrough. Today, we reviewed the problem count substrings that differ by one character and discussed its brute force solution. Remember, mastering substring operations and complexity analysis is key for string problems. Keep practicing, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!